Okay, in previous lectures, we talked about the antenna parameters, some antenna parameters from circuit viewpoint. So remember, antenna is a transition device between this side, which is circuit side, and this side, which is the space side. So we talked about some of its parameters from the circuit side, like impedance, reflection coefficient, VSWR. And now we're going to focus on some of the parameters on the space side. And we're going to start with radiation pattern of the antenna. So radiation pattern of the antenna. So that actually means how the antenna radiate as a function of angles within the space. So for example, if I have this dipole antenna and I give it, for example, some amount of watt, let's say 1 watt, I want to know how much it radiates in this direction, how much it radiates in this direction, how much it radiates in this direction. So I want to understand the relative power that it radiates compared to the maximum power in a certain direction. So essentially, you want to understand the distribution of the radiated power in a space. Maybe in some direction it's maximum, maybe in another direction is minimum. And this type of concept would be essentially radiation pattern of the antenna. So to understand the radiation pattern, we need to understand a spherical coordinate, because most of the time we're talking about theta and phi when it comes to radiation pattern of the antenna. So before going deeper into radiation pattern, let's understand a spherical coordinate. So to understand the spherical coordinate, let's assume that this is z-axis, this is x-axis, and this is y. So if I consider any point here, this point that I have in a space, if I connect it to the origin, the angle between this connection from the point to the origin and the z-axis is my theta angle. And if I project this point on the xy plane, like this, for example, now I'm on the xy plane, and then I connect the projection on the xy plane to the origin, and if I consider from the x-axis, this angle is phi. So this angle is theta and this angle is phi. So this point in a space has certain distance from the origin. This is r, and then this angle, which is my separation from the z-axis, is theta, and if I project it into the xy plane, then the angle from x-axis is phi. So essentially, if you have a point in Cartesian coordinate x, y, z, the corresponding thing in a spherical coordinate is r, theta, and phi. So this is distance, so in terms of meter, and these are angles that I have. And radiation pattern essentially shows how the radiated field or power from the antenna changes as a function of these two angles, theta and phi. So this is essentially, you have the field, for example, electric field or power, which is related to electric field square, as a function of theta and phi. So as a function of theta and phi, you have that in different direction, and you realize why we prefer a spherical coordinate, because it is based on angle. So if I, for example, say theta equal 30, so what does that mean when I have a dipole antenna? Assume that dipole antenna is in the z direction, so this is z. What is theta equal 30? Theta equal 30 means 30 degree with respect to z. So if this is z, so 30 degree is this. So if I now rotate this pen around here, all of this point is theta equal 30. So essentially a cone around the antenna. These are all theta equal 30. So, and what is theta equal 90? If this is again z, with respect to z, you come here, theta equal 90. Now you start rotating that, so this whole plane is theta equal 90. Of course, it is now more than 1 point because I'm just setting theta. But as soon as you also set phi, then you will have a specific direction. Then you say, this is my theta and this is my phi. For example, let's make an example. Let's say I'm interested to see theta equal 90 degrees and also phi equal 90 degrees. So what does theta equal 90 degree mean? Theta equal 90 degree means if this is your z-axis, you need to be away from z-axis by 90 degrees. So imagine my body is z-axis. So my body is z-axis, and I'm now, if I have my hand parallel to my body like that, it is at theta equals 0, theta equal 10, 20, 45, and 90. So this whole plane is 90, theta equal 90, because now my hand with respect to my body is at 90 degrees. So this pen is along my body and this hand is 90 degree between my hand and my body. So this is our theta equal 90. So as soon as I say theta equal 90, I'm on this XY plane and this side too and everywhere. So this is my theta equal 90. That means you come 90 degree here. But now, if I say phi, for example, let's start with phi equals 0. Phi equals 0, it means, again, my body is z-axis. So this is the theta variation, theta equal 90. So now I'm covering the whole plane here, theta equal 90. Now I need to set my phi. Imagine, for example, this direction is x-axis. So I'm on this plane, that's theta equal 90. And if I'm on x-axis, phi is 0. So remember, everything is with respect to x for phi. So you come with theta equal 90 to xy plane, and on the x, phi is 0. So if you say theta equal 90, phi equal 0, that means this direction. So if I tell you the radiation pattern, you want to figure out what's going to happen along the x-axis, you need to set theta equal 90, phi equal 0. If you want to check somewhere on the y-axis, again, theta equal 90, bring you down to this plane. Now, where is y-axis? If this was x, y would be this hand. So if this is x, this would be y. So that's at phi equal 90 with respect to x. So you want to have theta equal 90 and phi equal 92. That would be y hat direction, unit vector along y. This would be x hat direction. So what if you want, for example, this direction? This direction is theta equal 45. So if again my body is z-axis, this is now theta 0, you bring it here, theta equal 45. But remember, this is not the only theta equal 45. I can make a cone with that. All of them are 45. So if I plot it here, for example, this is 45, then all the points on the surface of this cone are theta equal 45. But if you only want this direction, so of course you want to be on theta equal 45, but you also know that this direction is on the y-axis. So phi is equal 90 from here. So this direction would be theta equal 45 and phi equal 90 degrees. So you see, by playing with theta and phi, we can go to different directions. Usually, it's very simple. So usually we said we get only two main cuts of the pattern, as we're going to discuss later. But generally, with variation of theta and phi, you can cover different parts of the 3D space. Now, according to definition of a spherical coordinate, theta varies from 0 to 180. So essentially, again, if I'm z-axis, this is theta 0, this is theta 90, and if I bring it all the way down, this is now theta 180. So I'm covering 0 to 180, and phi is 0 to 2 pi. So phi is from 0 to 360. So if my hand is now x-axis, so imagine this way is x-axis. Now, if I start rotating my hand, now phi is 90. Now, if I go here, phi 180 with respect to the x-axis. If I go here, is phi is equal 270. If I come back again to the same x-axis, it's 360. So this is the variation of theta and phi that we have in a spherical coordinate. So essentially, a radiation pattern tells us that how the fields of the antenna is in different direction. So that would be a three-dimensional radiation pattern. Okay, just before continuing, let me make another example to make something clear. So based on what I said, you remember I said theta equal 90 and phi equals 0. That's x-axis. So that's essentially positive x-axis. Then at this point, someone might say, okay, Puyan, why do you say theta equal 90, phi equals 0? Because if I'm on the axis, x-axis, this is x-axis, phi is always 0 because everything is with respect to x-axis. If my point is observation point is sitting on the x-axis, phi is already 0. So why you don't say phi equals 0 means x-axis? The reason is if you look at phi equals 0, if this is my z, this is my x, this is my y, you see all the points on this plane, every point on this plane, on the xz plane, all of them have phi equals 0 because imagine this point, right? This point has phi equals 0 because what's the definition of phi? You need to project it in the xy plane and it comes here. And then you look at the angle with respect to x-axis. Now, because it's sitting on the x-axis, it's phi equals 0. So if I again use my hand as the x-axis, so if I have a point here, here, or here, or here, so because I am the z-axis, this hand is x, all the points essentially on this plane would be phi equals 0. So all of them are phi equals 0. This point is here, phi 0. This point is phi 0. If you want to be specific, then you need to give the theta. So again, because my body is z, if I want to say x-axis, I know that phi is 0 because I'm on the x-axis, but I also need to be more specific so that I exclude this point, this point, this point, and only have the point on the x-axis. For that, I'm going to say my angular separation from the z-axis is 90 degrees so that I'm on the x-axis. Right, so you need both of them to exactly say which direction you want to be. So to do a little bit more practice in this regard, let's consider a couple of examples. For example, so if I tell you theta equal 90 degree, just theta equal 90 degree, what does that mean? Is it a specific direction? No, theta equal 90 means I'm z-axis, theta equal 90. This could be theta 90, this could be theta 90, this could be the theta 90. All the points in this plane are theta equal 90. So theta equal 90 is the same as saying xy plane. So with theta equal 90, you're bringing yourself to xy plane. What about, let's say, phi equals 0? Phi equals 0 essentially means you are on this plane. All of these points, if you project them, it's going to be on the x-axis. So all of them are on this plane. So this is essentially this plane that you have here. What about phi equal 90? Then you want to be on the positive side of the y-axis. So all the points here, these are phi equal 90. So as you see here, we have this situation that we need two of the angles to determine one specific direction, except only two axes. The one that we can do with one angle is essentially along the z-axis. So if this is my x, if this is my y, if this is my z, if I tell you theta equals 0 degrees, so again, if this is my body is z-axis, theta equals 0 means I have no separation with respect to my body. So if you consider my hand as the pointing to the observation point, now is theta equals 0. And this is only one direction. So when you say theta equals 0, that means you are looking toward positive z hat. And z hat means uh, unit vector along the z-axis. What about theta equal 80? That's also just one direction. Theta equal 80 essentially means the opposite of that. So instead of looking this way, which is theta equals 0, you come back 180 and you look the other way. That's theta equal 180, which is minus z hat direction. So except these 2 points, for other ones, we need to say what is your theta and phi. Okay, so far we've seen that we have our spherical coordinate based on theta and phi angle, and of course we also have r as a spherical coordinate. I'm going to talk about that later on, but essentially as you change theta and phi, you want to know how your antenna radiates in different directions. So essentially this is a 3D concept. So if I have my antennas like that, ideally I want to know in each direction, any direction, in 3D space how it radiates. But most of the time, as you're going to observe in the measurement aspect of our course, the video labs, we measure the pattern of the antenna not in 3D, but in two different cuts. And I'm going to talk about those specific cuts. So for example, if this is your dipole antenna, one of the cut that you might want to like to know the measurement is the horizontal cut, right? Or we may call it azimuth cut. So this cut would be essentially azimuth cut or horizontal cut. So if this is my z-axis along the antenna, so this plane that I want to know the radiation pattern is essentially xy plane because this was z. So in that case, I'm gonna if I plot xy plane, I want to know how antenna radiates in this xy plane. And if you look at this antenna structure and forget about this piece for transmission line, if you just look at the antenna itself, if you are here or here or here or here, you see the antenna the same thing. So you expect your radiation pattern to be something like that. So essentially, everywhere that you go on the XY plane, you see the same thing. So that would be the radiation pattern, but a 2D cut of the radiation pattern. And if you see something like that, you would say, oh, this radiates in this plane, essentially the same. And you might like this type of radiation pattern for some application. For example, in applications that you don't know where exactly you want to radiate. For example, in cell phone applications, you don't know exactly where you want to receive your signal or transmit. You might want to have this type of pattern in one plane to make sure that you have good coverage. So that would be one cut. And then the other cut that's sometimes very important, for example, for this specific antenna, would be a cut in this one. So if this is my z-axis, and let's assume this is my x-axis in this direction, so essentially you want to know the pattern in the zx plane. So this would be the cut that I want to know. So I want to change the point on this plane like that. So that would be another cut of the antenna. So if I plot, this is my Z axis and this is my X axis. And remember, this was my antenna. Antenna is along Z. I cannot plot the antenna here because antenna is like this, is in the Z direction. So if I make a cut, the antenna looks like a point. This is in fact your antenna along the Z axis. But here, because I have Z axis, I can plot my antenna. And for this specific type of antenna that I showed you, the pattern here would be something like this. So of course, these two should be identical theoretically. So what does that tell us? The most important thing that it tells us is that the maximum radiation happens in this direction toward the x-axis in this plane, and the minimum radiation, which is your null, is along the z-axis. So if I bring this antenna again, so what I showed you here was x is this x-axis and this is z-axis. So along the x-axis you have your maximum radiation, but then along the z-axis you don't have any radiation. You essentially have null. So if you want to use this antenna to communicate in this direction, that's a mistake, because this antenna has extremely small radiation and theoretically zero radiation along its axis. And most radiation happens in this direction. So this is something that you should keep in mind, that this radiation pattern is gonna tell you. And something I want you to notice here is that this point here, which is on the x-axis, is exactly the same as this point. So remember, these 2 points are exactly the same. So let me tell you again what we did in the first case. We plotted the radiation pattern on this plane. So for example, this point was here. So imagine if this point is point A. So we started from point A and we went this way. So that was our point A. Now, in the second measurement here, we started from this point A, but then we went this way. So if you look at here, the radiation of the antenna here and here are identical. And the reason I'm saying this is that this is something that you can check your measurement when I'm showing the video labs later on. If I measure, for example, 1 here, or any number, let's make something, let's say 0.8 as the maximum. So if this is 0.8, this is also should be 0.8, because they're the same thing, but it usually doesn't happen because of so many things that I explain in the video lab. But they need to be relatively close because they're the same thing. It's just 2 cuts, but that point is shared between those 2 cuts. So this is something that you can check as if your measurements have been done correctly or not. If they differ so much, let's say more than a certain number that I explained in those videos, then you may want to repeat your measurements and figure out what's going on. So that's one thing that I wanted to mention. This is so we call them 2D radiation pattern. So these are 2D radiation patterns. These are not 3D, but these are 2D radiation pattern. And why we consider 2D? Simply because measurements of 2D radiation patterns are easier. If you use simulation software to get the pattern, it doesn't matter, you can get the 3D radiation pattern, and I'm going to show it to you. But when it comes to measurement, it's usually difficult, so we usually get cuts of the radiation pattern. So the other thing about the radiation pattern is that what in fact we are plotting. So usually we either plot, so in these plots that I have, I either plot magnitude of electric field or power. So it's either magnitude of electric field or power. For example, so it, your measurement are either field measurements, which is the electric field measurements often, or they're measuring the power received by receiving antenna. For example, if this is your radiating antenna and you want to get point A information, you're gonna put another antenna here and you're gonna receive what's the signal here. Now, is this signal electric field that you're receiving? Then if that's the case, then you have what you are getting is a field pattern. If the signal that you're collecting here is the power received here, then it's power pattern. So you have this field pattern or power pattern. Now, which one do we use? It doesn't matter much because of the reason that I'm going to tell you. Now, if you measure that, if you measure these field pattern or power pattern, and when you want to plot them, one way that's right now that's going to be what I'm going to discuss. One way is to normalize it to the maximum value and then plot it. So, for example, imagine that you get your maximum here. So that would be maximum of Emax. So then when you are getting other points, you get other value, but at the end, what you do is that you normalize this radiation pattern. So now you get the same thing, but this time this would be Emax divided by Emax, and it would be 1. And this point before was something else, but now it could be just maybe 0.5. So everything would be a smaller than 1 because you are normalizing it. So this is called normalized radiation pattern. You normalize it to the maximum. In this case, I talked about field pattern. So it's a normalized radiation pattern. So if you are measuring power, so if this is power pattern, so this is Pmax. You measure the maximum power received. So what you do is that you're going to normalize that. And this point, after normalization, becomes Pmax divided by Pmax becomes 1. And then you get your other point divided by Pmax, and you get normalized power pattern. So maybe I can call this, I can ignore radiation because we know it's going to be radiation. So the first one was normalized field pattern. The new one is going to be normalized power pattern. So, and the same thing about that. So if you do that, when you normalize that, you essentially get a circle with the radius of 1 because it's going to be normalized. Now, the thing is, we usually show our pattern in dB. So, and the reason we show it in dB, I'm going to show to you the comparison between not showing in dB and showing in dB. The main reason is that you can see a smaller thing more clearly, because otherwise those smaller things, you're going to miss them. So let me tell you, give you an example. Imagine you have your main beam, because we normalize it, it's going to be 1. And then you have a direction. At that direction, you have very small value in your pattern. For example, look at here. This is theoretically 0, but let's say in a situation is 10 to the power of minus 5. 10 to the power of minus 5. Now, and I'm talking about, for example, power here. So if you plot that, you essentially don't see 10 to the power of minus 5 because it's much smaller than 1. And so here you only see one null, but in some other cases, you might see a few of them. For example, imagine this structure, for example, imagine this type of pattern that you might have something like this, and then another one So, so something like that. So it should be symmetric, but I plotted in a bad way. But forget about this one. But imagine this is 1. This is 10 to the power of at this point, is about 10 to the power of -5. And maybe here is 10 to the power of -4. So now, if you look at these things, uh, if you plot them together, these two are so small compared to that, that these two would be seen the same to you. You cannot appreciate between the difference between these two. But then if you change this to dB, so dB would be 10 log base 10 for power. So 10 log base 10 of 1 would be 0 dB. This becomes 10 log base 10, 10 to the power of -5, minus 50 dB. And then 10 to the power of -4 that I had here, 10 log base 10, 10 to the power of -4, minus 40 dB. Now compare the range here. Now you can actually see them very clearly. So you actually see them, you see a small numbers better. And in antennas, we usually want to see those small numbers because they correspond to our nulls, side lobes, and I'm going to define them later on. So that's why we show them in dB. Now, back to our discussion about field pattern and power pattern. Now, if we plot them in dB, they're going to be essentially identical. Now, let me tell you why. So you see, if you have a field pattern, a normalized field pattern, you have magnitude of E divided by magnitude of E max. That's a normalized field pattern at different locations. What about normalized power pattern? You have P divided by P max. And of course, they're different because, as you remember, power is related to electric field square. So power is related to magnitude of electric field square. So if I take dB of this, it's going to be 10 log 10 of this. So that would be my normalized power pattern in dB. If I plot P divided by P max, the maximum value is 1 because it's normalized. If I do 10 log 10, the maximum value is 0 dB. Log of 1 would be 0. Now, if you do dB for field pattern, remember, whenever you want to calculate dB of voltage, like S11, for example, was voltage, is 20 log. And electric field is like voltage, is volt per meter. Anything power is 10 log. Electric field or voltage are 20 log. So you have 20 log base 10 to convert that to dB. And you know that you can break 20 in 10 times 2. And if you bring 2 into the log, that essentially becomes to the power. And you know, then when you have electric field squared, that becomes equivalent to power divided by power, maximum power. So essentially, if you convert them to dB, this field pattern and power pattern becomes the same thing. So that was an introduction about radiation, 2D radiation pattern at this point. And one thing that I wanted to add, and I forgot to add, and is about angle variation. So let me go back to my plot that I had originally here. So this was my plot in the XZ plane. This was in the XY plane. Now, if you look at this pattern that I have here, what happens here is that I'm changing phi and I'm observing my radiation pattern, how the antenna radiates. Right now, when you are here, what is your phi? You are on the x-axis, phi is 0. Here, phi is equal 45 because you're changing with respect to x. Here, phi 90. Here, you get at 90 plus 45, 135. Then here, phi is 180. You get here phi equal 270. And you come back here, phi becomes 2 pi, which is phi equals 0. So here you're changing your phi. What is your theta? Your theta here for all of these points is 90 degree. If you remember, we mentioned that on the xy plane, theta is equal 90. So all these points that we observe in the radiation patterns, this one correspond to theta 90, phi 0. This one, theta 90, phi 45. But when I go to this one, the situation is a little bit different. And if I ask you what is theta here, what is the angle on the z-axis? This angle that I have now is theta equals 0. Now, what about this angle? So what about this point that I'm observing the radiation pattern? This is, of course, as you see, theta is 45. But remember, theta 45, again, if I'm the z-axis, this is 45, but all of these would be 45. It's a cone around me. All of them are 45. But you are talking about a specific 45, the one that's just above x-axis. So if this is x-axis, you're talking about theta 45 just above x-axis, which is this direction. So you want to say this is 45, but you are also just on top of, just above x-axis. So this is theta 45 and phi 0. Now, what about this point? This point, again, you're changing your theta to come 90 degrees, but not any 90 degrees, because again, theta 90 degree could cover the whole xy plane. It's again phi 0. So again, phi equals 0. Then if you come here, then now your theta is 135. So theta is 135. But remember, not any, 135 is a cone again. But you're talking about one specific one, the one that's just now below x-axis, which is phi 0 again. So you see here, these phi, they don't change. You're changing your theta. So this is at different angles. This is your radiation pattern. Now, if you go to the other side, now the only difference is that instead of having phi equals 0, because you are on the other side of the x-axis, your phi is equal 180. So that's the angular dependency. So you're telling how your antenna radiates with respect to different angles. Okay, so we talked about radiation pattern of antenna a little bit. In particular, we talked about 2D radiation pattern. I'm also going to talk about 3D radiation pattern, but not just yet. So let me remind you, that was our dipole antenna, and this 2D radiation cut is in the XZ plane. So the red pen is X direction, and the black pen is Z. So in the XZ plane, this is the radiation pattern that I have, which shows that along the axis of dipole, I don't have any radiation. So if you want to communicate in this direction, that would be the wrong way. If you want to communicate in this direction, you need to rotate the antenna like this so that you can communicate in that direction. So, but now imagine that you want to perform this as measurement. So where do you need to perform this measurement? So if you have this radiation pattern, so where you actually need to perform this measurement? Is it going to be something like this everywhere if you measure it everywhere? Because remember, I'm on the XZ plane. So I can essentially have a probe start measuring here, or I can go farther and start from here and perform measurements, or I can go even farther. Where do I need to perform these measurements to say this is the radiation pattern of the antenna? The fact is this, and this is the amazing part about the antenna. So it actually does not matter. You're always gonna get this shape, but with only one condition. As long as you're in a certain zone, which we call far field zone of the antenna. So as long as you are in the far field zone of the antenna, and we're gonna define what far field zone is, then if you go, for example, like X meter away from the antenna and you measure, and now next time you go 10 times X or 100 times X and you measure it again, you get very similar results. So essentially, theoretically, you would get identical result. But of course, up to a certain value in measurements, uh, and you're going to get this. So it really doesn't matter at which distance you measure. In any distance that you measure, as long as you're in the far field, you get this shape, or a different shape for a different antenna, so, or pattern as we call it. And that's essentially why we call it pattern, because if I go X meter away, as long as I'm in the far field, or I go 10X, I'm essentially getting the same thing. So it's like a pattern of the antenna that at any distance you see the same pattern. So, but don't be confused about something. So let me make that clear what I mean. I'm getting the same thing. So imagine I am measure. This is my X and this is my Z. And if I want to measure that, I need to go around the antenna like that and measure it. So I do one measurement like that around the antenna. I'll go around the antenna and I get this. Now, if I go farther and I do another measurement again, as long as both of them are in the far field, then for the black one, I get this. And for the red one, I'll get also the same thing, but with only one difference. Let me plot the red one. So I'm going to get this. I'm going to get this. So this is identical to that. But remember, in terms of value that I'm getting, for example, if this is, for example, let me make an example. If the value that you're recording here is, let's say, Emax at this point, when you are measuring here, of course you're going to receive less because you are farther from the antenna. And we're going to go to the details of math of this later. So it's not going to be Emax, because now uh, instead of being here, you are starting your measurements farther. So you have some signal drop. So instead of Emax, maybe you're getting 0.9 times Emax. So in terms of the value that you are capturing, they're not identical. But after that, if you normalize it, so now you're dividing this one by Emax, you're dividing this one by, of course, 0.9 Emax, because that's the maximum of this one. After normalization, they're going to be on top of each other, because both of them now has the maximum of one exact shape, similar, I mean, identical shape. So that would be what we call radiation pattern. If you are at this distance or this distance, it repeats itself. It does not mean that this value that you're receiving antenna, the probe that you put here to capture the electric field of the antenna here, would have the same value as that. So this is not what I mean. And that's why when it comes to radiation pattern, we normalize it, because we don't really care about this exact value. We just normalize it to tell the user that, look, this is the way that your antenna radiates. If the user wants numbers, we have a different mechanism for number, which I'm going to teach in a different video, and that's the concept of directivity or gain of the antenna. Then we get a radiation pattern with some very useful numbers. But these numbers, it's sort of useless for us, because I mean, it just means at what distance you measured your radiation pattern. And that's why in this case, we often normalize the radiation pattern and present it as a normalized value.